Welcome to the organic chemistry section of our practice MCAT questions. In this video, we're going to be going through questions 21 to 25. So first, I'll show you guys a question so that you can attempt them on your own. Here's question 21, 22, 23, 24, and 25. So just keep in mind the molecule that we're talking about in 25, it's the one that's drawn at the bottom. Okay, now we're going to go through the questions together. So in question 21, we're asked which of the following Lewis structures best represents oxoacetonitrile. So we have this given chemical formula, so the formula is a lot more important than whatever the name is. So based on that chemical formula, what is the best way for representing this formula? Well, whenever I see CHO, like the beginning of this chemical formula, I immediately think there's some type of aldehyde, and then the rest of it is whatever R group is given to us. And then in this case we do have CHO, so there's an aldehyde, and then we have a CN over here as our R group. So CHO is telling us that we have a carbon, a hydrogen, and an oxygen. And for this to make sense, carbon needs to have 4 bonds. So whatever is over here at the end, that's our R group. So one of its bonds is to the R group, which is CN. Another bond is to the hydrogen. And then if it has one bond to oxygen, it's not satisfied. It needs to have 2 bonds. So the answer to that is that it has a double bond to the oxygen, and we're talking about a carbonyl here, and then CHO is telling us that we're talking about an aldehyde. So in this case, the ones that are not aldehydes, we can remove those options. So option C we can remove because it's giving us an alcohol instead of an aldehyde. Also, it's important to note that its structure is not compatible with the formula that's given to us. We're given just one hydrogen attached here, and so if there's one hydrogen attached and one oxygen attached, I always think aldehyde. But in the molecule in option C, there are 2 hydrogens attached to that one carbon, so it doesn't really make sense. And then of course there's another hydrogen over here, and then there should be another hydrogen over here. There are way too many hydrogens in that molecule, so because of that we can eliminate it. And so one thing to keep in mind with Lewis structures is you want to show everything having a full set of electrons that it wants, so 8 electrons for most of the elements that are in the first 2 rows. So we want to draw it all out. Instead of just writing CN, we want to show that between the carbon and nitrogen in this nitrile group there's a triple bond, and then we want to show everything that has its lone pairs. So oxygen has 2 lone pairs and nitrogen has 1 lone pair. And so the one which completely shows all of this is option A. So A is correct. B is incorrect because it did not draw in this lone pair on the nitrogen. Because it's missing that lone pair, it's not fully representing how many electrons are present in a Lewis structure, and so that would be incorrect. And then D is incorrect because it's a bit similar to A, except for some reason it's as if this double bond moved over here, and then it's not clear where the triple bond electrons went to, because if they went to the nitrogen, then you would expect to see like 2 lone pairs on the nitrogen, but we weren't even given those lone pairs. So it's wrong for multiple reasons. First of all, why would this carbon have 2 double bonds? That can exist. Carbon having 2 double bonds, that's called a ketene. It can exist under some certain situations, but we're talking about in Lewis structures what's the most stable configuration of a given chemical formula. So it's unlikely that carbon would have 2 double bonds like this. So that's a problem. The amount of electrons around nitrogen, that's another problem. And then additionally we have another hydrogen over here, so we have 2 hydrogens when the chemical formula has only given us 1, and then oxygen is single bonded instead of that double bond. So a lot of problems, most problems with D out of all of the given structures. So D is the most off answer, and A is the only one that's the correct answer for this Lewis structure. Moving on to question 22. In 22 we're asked which of the following alkyl halides would most likely undergo an SN2 reaction. So most likely give us an SN2 reaction. for something to undergo an SN2 reaction, it needs to be attacked, and then it needs to have a leaving group that goes away. And so for whichever one of these is most reactive, we can think about it as whichever one has the best leaving group. And so all of these are halides, and you should know that halides in general are good leaving groups because they can exist on their own. So if they can exist on their own in solution and they don't necessarily have to be bonded back to the carbon, then that means that we do have a good leaving group. Like hydrogen, it can't really exist on its own as an H minus, as a hydrogen with a negative charge. So it's going to come back and reattach to the carbon. Therefore, it's not a good leaving group. But the chloride, it can exist in solution. So Cl minus, you do often see that in solution, usually has a counter charge. Like it could be H plus, it could be Na plus, but chloride, you've seen it often with a negative charge. It's fine with that. So chloride is a good leaving group. And then similarly, all of these are halides, so they're in the same group in the periodic table. Therefore, they display similar properties. So all of them are pretty stable on their own and they're fine as leaving groups. And so the other thing that we need to consider is what is the strength between carbon and these halides. And so that depends on things like the bond length, bond energy, all of that. And so things which would be strong are this carbon fluoride bond. So that would be pretty strong. Whereas the other ones, in between them, the worst would be the bond to the iodide, because iodine, that element, it has, well, of the halides, it is the one which is lowest in the periodic table, and then the trend is as you go down, the atomic radius increases. So in between carbon and iodine, there's a pretty big difference in their atomic radii, and so we have like something kind of relatively smaller bonding to something bigger, and so this bond, there isn't too much of a great overlap and similarity between the two atoms that are bonding. So it's not the strongest of the bonds, it's the weakest of them. And so therefore the best leaving group is iodine because it has the weakest bond with the carbon, so it's the most likely bond to be broken, and therefore it makes it the best leaving group. And therefore that answers our question, which one of these would most likely undergo an SN2 reaction? It's going to be the one in option C, because the iodine, it's the best leaving group. Now in question 23, we're asked, the molecule with the formula C7H14O2 could be which of the following types of compounds? So we have a given chemical formula. Which type of compound can it be? Can it be an ester? Can it be a carboxylic acid? Can it be a type of alcohol? So for this, you need to, well, the best thing would be to try to actually draw out some example molecules, but you can also have some hints from the chemical formula. So with the chemical formula, you know that if I had an ester, it would look like this. So it seems like this can reasonably exist because in the chemical formula we have two oxygens. So the key part that you should look at is the oxygens, because the oxygens directly relates to these different functional groups. So an ester is reasonable that we could make. It's a reasonable compound we could make from this chemical formula, because the key point is that there should be two oxygens available to us in the formula, because that's what the ester requires. And then after that, we can play around with moving around the carbons and the hydrogens to give us something which does match with this. So it's reasonable that an ester could be made. Carboxylic acid, under the same logic, it makes sense that as long as we have those two oxygens available, we can also make a carboxylic acid and then once again play around with the carbons and hydrogens to get the right structure. And then finally, an alcohol. Yes, we could also make an alcohol and then just add some more R groups to that. So because they specifically specify like a diol, yes, it makes sense that we could also make an alcohol. If for some reason they said an alcohol with only one alcoholic group, one like hydroxide group, then we couldn't make that alcohol because we should have only have O1, but we have O2, so two oxygens. But because they said it's a diol, yeah, it makes sense that we could reasonably make this compound as well. So for example, if one of the options was an amide, then you know that because there is no nitrogen in the chemical formula, that is not a functional group that you can reasonably make. So just try to think about that. Try to think about these things with that logic in mind, And then the actual answer that we have is yes. Okay, so the example of the compound got erased a little bit. Let me just fix that. But all of these compounds, it's true that they can be made. So here it is. Here is an example of an ester. Here's a carboxylic acid, and then here's our alcohol. So this is an example of all three of these functional groups with that given chemical formula, so 7 carbons and then 14 hydrogens. And therefore, since we can make all three of these, D is the correct answer for this question, because we can, with that chemical formula, have an example of all three of these types of functional groups. In question 24, it says that a new drug is developed and a pill called pill X is made up of 25% of this S plus configuration and 75% R minus configuration. It is found that the S configuration is actually the active form of the drug. Therefore, a new pill, pill Y, is developed which contains 100% S configuration. Which of the following holds true regarding these pills? So the main thing to keep in mind for this question is we have two pills. Pill X is 25% S and 75% R, okay? And then pill Y is 100% S. And then the rest of this information just kind of don't even really care about that, okay? So which of the following holds true regarding these pills? First thing to keep in mind, when we're talking about chirality, R and S is talking about the absolute configuration of just one molecule. So we have rules that we use for giving either R or S chirality that label to a certain chiral center, and we do that using the Kahn-Ingold Prelog rules. We will assign priority to the different groups attached to the chiral center, and then go in terms of like the decreasing priority, so from 1 to 2 to 3, with 4 being in the back. So we follow those rules, and then depending on whether that goes clockwise or counterclockwise, we say something is R or S. So that's talking about the absolute configuration when it's one molecule. But then when we have a macroscopic amount of that molecule, so when we have a solution of that one enantiomer of that chiral molecule, then we see the actual observed effects that it has on light. And then we say if it rotates light in one direction, then it's either plus or minus. So if it rotates light clockwise, so clockwise, that is plus, and then if it rotates light counterclockwise, that is minus. So it seems like the S configuration is clockwise, and then the R configuration is counterclockwise. Okay, so don't get that confused and always think that if something is R, it must be clockwise. That is talking about the absolute configuration of the groups of one molecule, okay? So as long as we know that, we can think now that pill X, it has 25% of S and then 75% of R. So it seems like R is predominating, and you should know with enantiomers, they rotate light in opposite directions to the same degree. So if we had like a 1-to-1 ratio of R and S, they would cancel out the rotation of the light. But in pill X, we have more so R, and so it like 25% of the R is going to cancel out the 25% of the S, and then the remaining 50% of the R is mainly just R, which is able to rotate light whichever way it does. So we're going to say that pill X is rotating light in the minus direction because of that R, and so it's going to be counterclockwise. And then pill Y, because it's 100% S, and we know that S has that plus configuration, it's going to be clockwise. Okay, so that's all we need in terms of the information from the question. Now let's get to the answers. Option A is saying that pill X rotates light clockwise, but no, that's incorrect because it is not clockwise, it is counterclockwise. And once again, this is because it's more so made up of R, and the the R configuration has that minus sign, so it's going to be counterclockwise. Option B is saying pill Y rotates light more clockwise than pill X. And yes, this is correct. So we established that pill X is mainly counterclockwise and pill Y it's 100% just clockwise. So option B is correct. Option C is saying pill X and Y will rotate light the same number of degrees, but they differ in the clockwise or counterclockwise directions. That is incorrect. That would only be correct if I had one pill which is 100% one enantiomer and another pill which is the other enantiomer. But we're not talking about two pure enantiomers here. Only pill Y is a pure enantiomer. Pill X is not a pure enantiomer. It is somewhat S and then somewhat R. It's not a full racemic mixture, so it does have some polarity, but it's not a pure enantiomer, and so we can't really say that statement is true, that they rotate light in the same number of degrees in opposite directions. And finally, in option D, it says pill Y rotates light counterclockwise, so just like option A, this is incorrect because it's just saying the opposite thing. So pill Y is actually clockwise. It might trip you up because you think S, and so it's counterclockwise, but once again, because of that plus sign in the S configuration, it is clockwise. Now in question 25, it says that the molecule below, once again, is drawn at the bottom of the page. It is this type of amide ester mixture thing. So it's synthesized in a lab if the 4 hydrogens, which are currently bonded to the 2 sp3 carbons, so we would be talking about hydrogens over here. If these guys are replaced with 4 fluorines now, which of the following best describes the acidity of the new molecule compared to the original? So when we're talking about acidity, that means that we are discussing the ability to lose a hydrogen, and the most likely hydrogen that we're going to be talking about is this hydrogen over here that's attached to the nitrogen. So we're not talking about acidity in terms of the hydrogens that are bonded to carbons, because just logically, based on your knowledge of how acidic hydrogens are, you should know that the ones bonded to carbons are really not that acidic. So these guys have been replaced with fluorines, and so therefore now really the only hydrogen remaining is the one with nitrogen, so it should be very clear that that's the hydrogen that we're talking about. Now, is this more acidic or less acidic? Well, you should always think about it in terms of what happens when a reaction takes place. Well, if an acidic reaction takes place, then you get a base being formed. So what happens is you get this negative charge on a nitrogen because that hydrogen was taken. So you get a conjugate base being formed. And then if the conjugate base is stable enough, then the molecule is going to be stable and it's not going to try to go back and be protonated back to the acid form. Therefore, we do have a strong acid. Otherwise, if the conjugate base is strong and then it goes back towards the acid, then the acid itself is not that strong. And so 2 factors are at play here. First of all, when I have an amide, I have the ability for resonance to take place. Okay, so that negative charge can be offset a little bit because it's donating into that carbonyl system, and so the negative charge is distributed between the oxygen and the nitrogen. So that makes the conjugate base a little bit more stable because it can handle the negative charge. But an important thing to keep in mind is that the addition of those fluorides really did not add that ability of resonance to take place. The resonance takes place because we had a carbonyl, because we're talking about an amide. Amides already always go through this resonance in between the nitrogen and the oxygen. That's just a key property of amides. And so adding those fluorides did nothing. So this is kind of irrelevant to what's going on in terms of the acidity. And so the main thing that we care about with the fluorides is they are pretty electronegative. And so therefore they're creating a polarity this way towards the fluorides. So the fluorides are pulling electron density from the carbon, and then as a result, now that carbon is pulling electron density from the nitrogen. So what's really going on is that new negative charge that was formed on the nitrogen is being pulled away from the nitrogen towards the different fluorides. So instead of all of that system at the top, now the electron density is being diverted downwards towards those fluorides as well. And so this just adds to the stability of the molecule. So before we could direct that negative charge away from the nitrogen now to the oxygen, so nitrogen isn't so unhappy that it has a negative charge. Now we can divert it even more so towards these fluorides, and then fluorine is very electronegative, and so therefore it wants to hold that electron density. So now nitrogen has to hold that negative charge even less so, and so because of that, because of this electronegativity or the inductive effect, now nitrogen is fine and the conjugate base is more stable. So we're looking for an answer like that. So it's going to be more acidic, not less acidic. So options B and D we can remove because they're talking about something being less acidic. Option A is saying it's more acidic, since deprotonation would now result in a better stabilized conjugate base. Yes, due to the electronegative fluorines providing an inductive effect. And yes, that's the key part here. When we're talking about adding fluorines or chlorines or anything like that in terms of how it affects acidity, it usually makes things more acidic, and it's due to the inductive effect. And then B is incorrect because it's talking about it being less acidic, and then it also is talking about something like the fluorines providing resonance to the nitrogen atom, but that's incorrect because, as we said, it's not the fluorines that have anything to do with the resonance system. C is incorrect because it says it's more acidic, but then just like with B, it starts talking about resonance, and that is irrelevant to what the fluorines are doing. And then D is incorrect because it's saying it's less acidic instead of more acidic. So correct answer here is A. That's it for the questions in this video. If you enjoyed what you saw in this video and you want to see a lot more questions and then us going through the different answers and explaining why each one is right or wrong, then make sure to check out our course, the 30-day MCAT prep course, which is available on teachable.com. The link is in the description below. Other than that, make sure to subscribe so that you see all of our upcoming videos. And that's it for this video. I'll see you guys in the next one.